Welcome to today's lecture. Uh, Today we'll discuss about different noise parameters. This noise parameter we need to study signal to noise ratio, noise factor, noise figure, okay, noise equivalent temperature, then narrow banded noise. These are the different noise parameters. So these things I'll discuss in two videos. So this is the part 1 video. So first, here we need to discuss about signal to noise ratio. What is signal to noise ratio? From the name itself we can understand it is the ratio of signal power to noise power. S by N ratio we normally call S by N ratio, that is signal power by noise power, that is signal to noise ratio. It is normally represented as S by N. Okay, S by N is equal to PS by Pn. PS is nothing but signal power. Pn is, we know that Pn is noise power. So S by N is nothing but PS by Pn. Signal power by noise power is signal to noise ratio. This signal to noise ratio is represented in dB. Normally it is represented in logarithm scale, and it is S by N in dB is 10 log PS by Pn. Okay, 10 log PS by Pn. Signal to noise ratio is important parameter for a system. It is normally represented in logarithmic scale. So in S by N dB is 10 log. We know that PS and Pn. What is PS? PS is power at signal power. That means power at signal input. Okay, power at input. It is normally represented, power is nothing but V square by R. So this is input. So V square by Rn. Okay, Rn is input resistance, Rout is output resistance, Vs is signal voltage, and Vn is noise voltage. So here S by N dB is equal to 10 log PS by Pn. PS is Vs square by Rn, and Pn is noise voltage, noise power. We know that Pn is Vn square by Rout. Okay, so this is generally the representation of S by N dB. Okay, so we know that normally input and output resistance of an amplifier or a receiver or a network being evaluated as equal. Suppose I am considering this input and output resistance are equal. So normally in system we consider input and output resistance are equal. This condition is called a maximum power transfer theorem. Maximum power transfer theorem means we have a source and we have a load. If we need to transfer maximum power from the source to the load, both the source and load resistance should be equal. That is a condition. Okay, we normally assume that this input and output resistance are equal. At that condition we can write S by N dB as 10 log Vs by Vn. Resistance cancel out, so 10 log Vs by Vn the whole square, or 20 log Vs by Vn. This is the signal to noise ratio in terms of voltage, and this is signal to noise ratio in terms of power. Next is noise factor and noise figure. So these are the two important parameters. Noise factor is normally represented as F, and noise figure is represented as NF. Okay, noise figure is NF. Noise factor and noise figure are figure of merits used to indicate how much the signal to noise ratio deteriorates as the signal passes through the circuit or a serial circuit. That means you have a circuit. Okay, you have a circuit and a signal passes to that circuit. Okay, a signal enters into a circuit and it get out from the circuit. Okay, what happens if the signal enters into a circuit? What happens if the signal get output from the circuit? This tells about this noise figure. So how much the signal is deteriorated as it passes through the system. Okay, signal is passes through a system, and how much that signal is deteriorates, that determines this noise factor or noise figure. Okay, so noise factor, first we need to study noise factor. Noise factor is equal to input signal to noise power ratio by output signal to noise power ratio. So it is actually the ratio of ratios. Okay, it is actually the ratio of ratios. Ratios of what? input signal to noise ratio by output signal to noise ratio, or we can write as Si by Ni by S0 by N0, that is noise factor F. And noise figure is represented as NF. It is simply the noise factor in dB. We know what is noise factor. Noise factor means input to signal to noise ratio by output to signal to noise ratio. Consider a system. System have an input signal to noise ratio, input S by N and output S by N. Okay. So consider this is a system. This is input, this is output. Okay. Output to signal noise power is S0 by N0. Input signal noise power is Si by Ni. Okay. So the ratio of this quantity by this is noise factor. Okay. And that noise factor expressed in dB, that is noise figure. Okay. So noise figure is simply the noise factor stated in dB. It is commonly used to indicate the quality of a receiver. So this factor indicates the quality of a receiver. So sometimes we need to check the quality of receiver. Sometimes in a system, if more noise are coming into the system, we call it as it is a low quality system, like that we will tell. Okay. So we always check for quality while designing a system. We need to check the quality of the system. If it is a good quality system, there will be less noise. So noise factor is a parameter used to check the quality of the system. So noise figure in dB is 10 log input signal to noise ratio by output signal to noise ratio, or we can call it as NF in dB is 10 log F. This is nothing but noise factor F. Take the logarithm of that, we will get a noise figure in dB. Okay. So noise figure indicates how much signal to noise deteriorates as the waveform propagates from input to output of a circuit. Okay, input to output of a circuit. See, signal enters into, this is a system, signal enters and leaves here. So as the signal enters into system, that signal is processed by the system and you will get an output. So what happens if how much the signal deteriorates as it passes through the system? This factor is determined by, or this is explained, that parameter is explained by this noise figure. Okay. So noise factor indicates how much signal to noise ratio deteriorates, how much S by N signal to noise deteriorates as the waveform propagates from input to output circuit. Example: an amplifier with a noise figure of 6 dB means that signal to noise ratio at output is 6 dB less than what it was at input. Okay. So assume that an amplifier has a noise figure of 6 dB. Amplifier has a noise figure of 6 dB. That means for example, this is an amplifier. It is having a noise figure of 6 dB. That means the output to signal to noise ratio S0 by N0 is 6 dB less than S0 by Si by N at input. Okay. Here it is 6 dB, that means here it is how much? 16 dB. Sorry, 6 dB less than the input. Okay. For example, here 10 dB comes here. Okay, and we call it as signal to noise ratio at input. What is the signal to noise ratio at output? That we need to check. Okay. So here I am taking 10 dB. Noise figure I am taking 6 dB. That means output signal to noise ratio is 6 dB less than the input. So 10 minus 6, it is 4 dB only at output. So that's why they are talking like this. An amplifier with a noise figure of 6 dB means that signal to noise ratio at output is 6 dB less than it was at the input. Okay. If the circuit is noiseless and add no additional noise to the signal to noise ratio at output will be equal to signal to noise ratio at input. Okay. If the circuit is noiseless and no additional noise is added to the signal, that means in the circuit there is no noise is added to the circuit, or it is a noiseless system, then both these factors are equal. Si by Ni is equal to S0 by N0. Under what condition? Under the condition that if the system is noiseless. Okay. So for a perfect noiseless circuit, noise factor is 1. Okay. That means, what is noise factor F? Input signal to noise ratio by output signal to noise ratio. If the system is noiseless, these two parameters are equal. That means there is no noise in the system. Whatever you give input, amplified signal you will get as output. Okay, so we are taking the ratio of these two. So these two are equal. That means F equal to 1. So for a noiseless system, noise factor is 1 only. What about noise figure? Noise figure is 10 log F. F is 1. So 10 log 1, 0 dB. So ideal noiseless system noise figure is 0 dB. In an electronic system, circuit normally amplifies signal and noise with its passband equally well. Suppose consider a system, a signal plus noise enters into the system. The system will amplify it. Okay, this is a system, and this is SI by NI. That means signal and noise both are coming into the system, and both the signal and noise are amplified, and you will get a signal to noise ratio 0 by N0 at output. The thing is, the system should not add any noise into the system. This is our system. Due to the thermal and thermal noise, all those things, flicker noise, short noise, we know all those things. These are the system noises. That system should not give any noise to the signal. 0 by signal to noise is normally comes into the system, and system amplify the signal and noise, and you will get an amplified signal noise ratio at output. But the thing is, the system should not give any noise into the system, into the signal or into the waveform. Okay. So an electronic circuit amplifies signal and noise with its passband equally well. Okay, the system will amplify both the signal and noise in its passband. Passband means what are the frequency range this system operates. That is the passband. Suppose this system is operated at 10 kilohertz, means up to 10 kilohertz frequency it will pass. Above 10 kilohertz it will not pass. That is the passband of this system. Each and every system is intended to operate a particular frequency. That is what is called its passband. Okay. So therefore, if the amplifier is ideal, noiseless, input signal and noise are amplified, and output signal and noise at output will be equal to S by N at input. See, if the system is noiseless, this is amplified, and I will get an amplified S0 by N0, and both are equal only. Amplification factor is there, that will cancel out each other. So we will get an amplified signal, but noise, there is no noise into the system. Okay. And how it is, we will check how it has happened. Okay. In reality, amplifiers are not ideal. Okay, amplifiers are internally generated noise into the waveform, reducing the overall signal to noise ratio. We know that practically we can't make an ideal system, so definitely the system noise will enter into the system. That means internal noise will be generated, and it will be added to the input. Most predominant noise is thermal noise. Okay, always. Our network amplifies and the system add noise to the signal, and thus reduce the overall signal to noise as the signal pass through it. That means, see, consider this system. This is the things what I am describing that I drawn in a box. So this is actually ideal noiseless amplifier. Okay, this is an ideal. There is no noise introduced by this amplifier. Okay, but no signal and noise comes into the system. See, actually signal and noise is signal plus noise. Those things comes into the system, and that is amplified by the system. Both the signal and noise are amplified by the system, and you will get an amplified output. But the system will not give any noise into the waveform. Why? Because this system is noiseless. What he will get, he will just amplify and boosted, and he will get an amplified boosted signal at output. But he will not give any, this system will not give any noise to the waveform. So SI by NI is the input signal to noise ratio. Output is S0 by N0. See, AP is the power gain. So both the signal and noise are amplified. That's why signal, if it is a parameter of 5, then signal multiplied by 5. 5 times it is signal is amplified. Noise is also 5 times amplified. That's why it is written like that. S0 is 5 times SI. N0 is 5. 5 means here it is power gain AP. So AP into SI, AP into NI. So both these parameters are cancelled out. You will get SI by NI. That means Output signal to noise ratio is nothing but SIA by NI, that is input only. That is why it is written like that. If the amplifier is ideal, noiseless, input signal to noise ratio, input S by N is amplified, the output S by N will be equal to S by N at input. That means if the system is noiseless, that means output S by N ratio is, input signal noise ratio is amplified by this factor. Okay, so 0 by N0 equal to AP into SI by NI. AP is multiplied by both numerator and denominator, so it will be cancelled out, so we will get as SI by NI only. That means output and input are equal. That means here figure noise factor is 1, noise figure is 0 dB. What about this system? Practical system is non-ideal amplifier. We have a non-ideal amplifier in practical. So AP is power gain, ND is the internally generated noise. That means this is the practically we can't make an ideal system. So definitely noise will be there in the system. So as like signal to noise ratio is enters into the system. So this is amplified by a factor of AP plus noise is added. That's why it is written as 0 by N0 equal to AP into SI by AP into NI plus a noise, that is system generated noise, that is ND. Okay, then AP take out and cancel out, we will get a 0 by N0 equal to SI by NI plus ND by AP. So 0 by N0 equal to SI by NI plus ND by AP. Okay, so output signal to noise ratio is less than input noise ratio, input signal to noise ratio by an amount proportional to ND. Okay, in ideal case both are equal, but in practical case this is output signal to noise ratio is less compared to input by a factor of ND. Okay, so that means output signal to noise ratio is less. That means signal to noise ratio is less means this entire quantity is decreasing, or less means top numerator we have signal power, denominator we have noise power. Okay, this entire factor, entire ratio is less means signal power is less. That means we will get a less amplitude signal. That means we will get a feeble signal at output, so we won't be able to hear the sound if we are transmitting an audio signal. Okay, now consider n number of amplifiers are cascaded. Cascaded connection means output of one amplifier is tied to another amplifier, input of another amplifier, output of another amplifier is tied to input of next amplifier. This connection is called a cascaded connection. Okay, so in cascade I am connecting n amplifiers. Each amplifier have gain AP1, AP2, etc. APN. Noise figure is NF1, NF2, etc. NFN. So total noise figure is NFT. Okay, so input signal power is SI by NI, output signal power is S0 by N0, which is equal to SI by NI plus total noise factor NFT. So when two or more amplifier cascaded, total noise factor F is accumulation of individual noise factor. Okay, so in this cascaded connection, total noise factor is the accumulation of individual noise factor. Okay, Frill's formula is normally used to calculate the noise factor F. If several cascaded amplifiers are there, we use Frill's formula to find out the total noise factor. So total noise factor according to Frill's equation, Ft is equal to F1 plus F2 minus 1 by A1 plus F3 minus 1 by A1 A2 plus etc. plus Fn minus 1 by A1 A2 etc. An minus 1, where Ft is the total noise factor of cascaded amplifier, F1 is the noise factor of amplifier 1, like that Fn is the amplifier of noise factor of amplifier n. AP1 is the power gain of amplifier 1, etc. APN is the power gain of amplifier n. So noise figure represent as NFT total in dB is equal to 10 log Ft. Ft total is noise factor total. So take the logarithm, we will get a noise figure total. Okay, look at equation 1. From equation 1 it can be seen that first stage in series of amplifiers contribute the most to overall noise figures. Okay, first it can be seen that first stage of series of amplifier contribute most overall noise figure. See, look at equation ft is equal to f1 plus f2 minus 1 by 1, like that it is going. So total noise figure is contributed by the, mostly it is contributed by the first amplifier circuit, first amplifier circuit f1. Why? Because the remaining times it is subtracted by 1 and it is divided by the gain a1 a2, like that it is, the entire time is divided by, noise figure is divided by gain. But in first time there is no division time, so the entire noise factor, it's mostly it is contributed by the first amplifier noise factor. Okay, so this is about noise figure and noise factor. Next we need to discuss about noise equivalent of temperature, that we will discuss in the next lecture.